Okay, so welcome everyone and thanks for attending this talk. I've seen that most of the room left for the real-time recommendation or some other talks, but thanks for coming. We'll talk about something really closely related to real-time recommendations. It's about live queries. But first, I'm a researcher from Hungary, from the Budapest University of Technology and Economics, and I'm also a visiting researcher at the McGill University in Montreal. So, what are live queries? Let's imagine a railway network, for example. This is a prime example of a safety-critical cyber-physical system, because in such a system, we work very hard to ensure that no accidents happen and no equipment is damaged. So, in such a system, we would like to check a lot of constraints continuously to see if the system works properly. This system consists of a couple of segments, a couple of trains, and obviously these trains are moving along the tracks. And in such a system, we don't want the trains getting too close together for obvious reasons, so if there are trains that are on adjacent segments, we would like to issue a warning that they are in too close proximity. Also, in the railway system, there are switches. The switches may be in a straight or diverging position, and there is a very interesting constraint in railway modeling, is that if you have a switch which is in a diverging position, you cannot go from the opposite direction at full speed because that might damage the switch. This is called trailing the switch, which is very expensive, and we would like to avoid that as well. So, how do we begin this? We can model this as a graph pretty intuitively. We just assign a node for each segment, a node for each train, and then add edges that a train is on a particular segment. The segments are connected to the next, and so on. And once we have this, we can capture the constraints with graph patterns. So for example, the proximity detection can be captured by a simple graph pattern that says that if there is a train that's on a segment and there is only one or two next edges between the next segment that has a train, then we issue a warning. We can formulate this in Cypher pretty easily. Cypher is quite easy to write and read, so this will be our Cypher query. And if we have a Cypher-compatible engine like Neo4j, it will generate a nice query plan and evaluate this quite efficiently. Also, for the trailing the switch constraint, we can add a graph pattern that there is a train which is on a segment which goes straight to a switch. This can also be captured with Cypher that has a match and a filtering operation. And again, Neo4j is capable of evaluating this easily. However, in a real system, we have a huge graph with millions of nodes and edges. We have dozens of complex patterns, and we would like to monitor this system 24/7 continuously. So we would like these queries to be continuously evaluated. This leads us to the idea of live queries. Traditionally, databases have batch queries, which means that the client issues the query, the database calculates the results, and then the results are returned on demand. On the contrary, live queries are calculated continuously. First, the client registers a set of queries, and upon each change, it maintains the results. So basically, the latest results are always available, and the client is able to receive notifications from the server. So this leads us to the idea of incremental query evaluation. These can be used for live queries. Incremental query engines have been around for decades. There are tools that were developed at NASA, the CLIPS system, the DRU's rule-based expert system, and there is also Vietra, which was developed at my university, but is now an industrial-grade tool developed by Inquiry Labs. Also, there are a couple of academic projects, like the instance system for semantic graphs, the i3quell system, and my early PhD project, the InquiryD project. So, if you observe this site closely, there are a couple of things to notice. The first is that industrial projects have their cool logos. The second is that academic projects are written in cool functional programming languages like Lisp and Scala. But more importantly, there are no implementations for property graphs yet. So we decided to create ingraph, which is a proof of concept implementation for a continuous query engine. And we would like to make ingraph in such a way that it's able to operate distributedly and in parallel. So in the big picture, this is how it looks like. There is a client. The client registers a set of queries, receives the results, and upon each change, the client will receive the changes that the latest updates introduced in the system. So how does it work under the hood? There is some complicated caching involved, and this is how it works. If we look at the trailing the switch example, we formulated the graph query that's on the left, and we created this network which caches the interim results of that pattern. The way this works is that we use indexing for gathering the edges and the relevant nodes of the graph. So first, we gather the on edges, then we gather the straight edges, and using these indexes, we build up the partial matches of the graph. So first, we create the triples with the train, the segment, and the switch. And then we select those switches that are in the diverging position, and then perform the projection to the train's number and the switch. Now this is great because if we have a small change in the system, for example, the train moves from segment E to segment D, like so, then we only have to propagate these changes, so delete the previous tuples, add the new ones, and propagate this through the network, which is much cheaper than completely recalculating all the query results. And now we have no results, which is very good news because we were checking for errors in the system. Now the train won't trail the switch. Okay, so from a programming perspective, this is a very good approach because you can model these boxes as actors in a distributed system, and we can model the message propagation as immutable asynchronous messages. So this means that this can be done in a parallel and distributed fashion quite easily. We actually have a paper from 3 years ago at the Models Conference where we showed that this indeed scales quite well for large RDF datasets. So how does the system look architecture-wise? Well, first we needed a query language, and this wasn't a trivial question 2 years ago. Fortunately, it now is because Neo4j started the Open Cypher initiative, which provides a language specification for the Cypher language, including the specification for the grammar, a large test case called the TCK, and also the Cypher language specification, which is an informal document containing the language features. We wanted something more formal, so when we started working on this, we formulated the Cypher query language in relational algebra. This is quite a complicated mapping. We submitted a paper to a database conference and made the preprint available on Archive. I hope that this will be useful for people who would like to implement Cypher or are simply interested in the internal quirks of the Cypher language. So once we had this, we pretty much followed the textbook on building a query engine. So we have our query, we parse it to a syntax tree using an xtext-based grammar. We build a relational graph algebraic expression using our compiler. And once we have this still needs some care because we need to transform it to something that's incrementally maintainable. So we use a transformer and optimizer to do this. And interestingly, if you think about it, the query plan itself is only a graph, and the incremental query plan is a graph as well. So basically, we use graph transformations to do our query plan. And this is done by the Viatra tool that I just mentioned. So we are using an incremental graph query engine to drive our incremental graph query engine, which I think is pretty cool, and it works quite well. So once we have the network, we just deploy it to a Scala-based implementation and hope it works. There are two use cases that I would like to highlight. One of them is constraint checking in model-driven engineering. This is closely related to the railway use case that I used as the running example. Basically, in model-driven engineering, there are very complicated constraints that must be kept during development. We designed a benchmark that has a large synthetic model generator that's able to generate models with tens and millions of elements. We formulated a couple of validation queries and transformations, and we tested systems from all technological spaces that are related, like semantic webs Eclipse modeling, relational databases, and of course property graphs. This is available as an open access paper, so you can go to Springer and download it, and also the source code is open source. Another example is the static analysis of JavaScript code. This is an increasingly important topic because JavaScript is getting more and more widespread, and static analysis can help us prevent issues in the code, such as this one. We build a syntax tree from the JavaScript code, which is then queried by Cypher queries, and we return the results that might cause an issue at runtime. This is a very good use case for incremental graph query engines because these graphs are huge, the patterns are complex, and the graph is continuously changing, but only by a small amount because developers typically save and commit just a couple of lines of code. So we currently support ECMA script 6, and we have cool features like dead code detection and basic time inferencing on vanilla JavaScript code. So to summarize, please consider using live queries if you have a large graph with continuously changing data and complex patterns. Also, our current goal in the development is to support as much as OpenCypher as we possibly can, and we plan to use the Linked Data Benchmark Council's social network benchmark. I'm a member of LDBC, and we are working on a next benchmark which defines a business intelligence-like workload, which will be a very good use case for ingraph. And also, we are looking for more use cases, especially example datasets and fraud detection queries. If you have such a use case, please come and do talk to us. We are very interested in working with you. Thank you very much.